In a previous video, we calculated the distance at which our planet orbits its star. This is sufficient for a simple build, but for a more accurate, detailed build, we need to define a few extra parameters, namely its inclination, eccentricity, periapsis, and apoapsis. Don't worry if you're not familiar with these words, you will be by the end of this video. The first parameter that we're going to define for our planet is its orbital inclination. This is just the angle at which our planet's orbit is tilted relative to some reference plane. Now, what you use as the reference plane is up to you, and you have a couple of options. One option is that you can use the equator of your system's star to define the reference plane. This is the method that I prefer to use as it's simple, intuitive, physically significant, and keeps you from having to define an obliquity for the star. But alternatively, you can use the orbit of one of the planets in your system to define the reference plane. This is what modern astronomy usually does, using Earth's orbit around the Sun to define the reference plane. This necessarily gives Earth an inclination of precisely 0 degrees, and all other planets in the solar system have their inclinations measured against this. If you use this method, you can use any planet in the system to define the reference plane. It can be the primary inhabited planet, or the planet closest to the star, or anything else that makes sense to you. The reference plane is important for other things beyond just the planet's orbital inclination. Later, when we define the obliquity of our planet, that is, the tilt of its rotational axis, the angle can be described relative to both the planet's orbital plane and the system's reference plane, if these two are different. And if the planet in question has a moon, in order to really understand that moon's orbit, we need to know how its inclination relates to the planet's obliquity, the planet's orbital plane, and the system's reference plane. So the reference plane is definitely something that you need to define, as it's crucial to understanding the orientation of the objects in your system. Once you've chosen your system's reference plane, you need to define your planet's inclination relative to it. If you've chosen your planet's orbit as the reference plane, then its inclination is 0 degrees. But if you've used the orbit of a different planet or the star's equator as the reference plane, then your planet will have some non-zero inclination angle. The planets of most stable planetary systems will have relatively low inclinations relative to the star's equator and to one another. This is usually less than 10 degrees or about 0.17 radians. If a planet's orbital inclination is significantly greater than this, it's usually a sign that something major, and likely catastrophic, has disrupted the system. I'm going to set my primary inhabited planet's orbital inclination to 3.2116 degrees, or about 0.056 radians, relative to the stellar equator, and then record this on my SAP sheet. The next parameter we can define is our planet's orbital eccentricity. This is just a measure of how elliptical the planet's orbit is, and is given as a number between 0 and 1, with 0 being a perfectly circular orbit and 1 being a parabolic trajectory. All planets will have some amount of eccentricity in their orbit, but most planets possessing a stable climate will have nearly circular orbits with an eccentricity below 0.05, with the extreme limit for habitability likely around 0.15. It is extremely rare to find any planet with an eccentricity higher than 0.5. For reference, Earth has an orbital eccentricity of 0.0167. High eccentricity is often the result of a planet having its orbit distorted by the gravity of a nearby, more massive object, such as a gas giant or a secondary star. For example, Mars's eccentricity of 0.0934 is due to Jupiter lying adjacent to its orbit. Likewise, Mercury's very high eccentricity of approximately 0.2 is due to Venus and the rest of the planets in the solar system tugging on its orbit. So if your planet has a more massive object orbiting nearby, then it will likely have a significant eccentricity. But if your planet sits comfortably in a spacious orbit well away from less massive companions, then it will have a near circular orbit and low eccentricity. I'm going to give my planet an eccentricity that's slightly higher than Earth's, but still considered near circular, of 0.0228. Now that we have defined the eccentricity of our planet's orbit, we can calculate how close and how far it passes from its star while following its elliptical path. We'll start with our planet's minimum distance to the star, a parameter known as the planet's periapsis. To calculate this, we can use this equation, which relates the periapsis to our planet's semi-major axis, or its average orbital distance, minus the product of the eccentricity times the semi-major axis. So I'll open up my calculator and start by entering in my planet's semi-major axis, which we calculated in a previous video. For me, that's 128,405,977,376 meters. Then I'll subtract and open parentheses. I then enter the eccentricity that I just defined, 0.0228, and multiply. Then I enter my semi-major axis again. Then close the parentheses. Your equation should look something like this. We press equals, and there's our planet's periapsis distance in meters. So I'm going to add that to my SAP sheet as 125,478,321,092 meters. Before we move on, let's convert this value into astronomical units by dividing it by 149,597,870,700 meters. That gives me a value of 0.8388 astronomical units. Next, we'll calculate the maximum distance the planet reaches from its star, a parameter known as its apoapsis. To calculate this, we can use this equation, which relates the planet's apoapsis to 2 times the eccentricity times its semi-major axis, its average orbital distance, plus its periapsis distance, which we just calculated. So let's go back to the calculator and start by entering 2 times our planet's eccentricity. Mine is 0.0228. Then multiply by the semi-major axis distance. For me, that's 128,405,977,376 meters, plus my periapsis distance, which I'm going to recall from the calculator history. So your equation should look something like this. Press equals, and there's our apoapsis distance. So I'm going to add that to my SAP sheet as 131,333,633,660 meters. Once again, before moving on, I'm going to convert my value into astronomical units by dividing it by 149,597,870,700 meters. This gives me a value of 0.8779 AU. If you've made it this far, congratulations. You now have a very accurate description of your planet's orbit. Before I end this video, I want to calculate 2 additional optional parameters for my planet, its minimum and maximum orbital velocities. To do this, we can use this equation, which relates the square of the instantaneous velocity to the standard gravitational parameter times the remainder of 2 divided by the planet's distance from the star minus 1 divided by the planet's semi-major axis. We call this the instantaneous velocity because this equation calculates our planet's velocity at just 1 instance in its orbit. The velocity of an object changes as it follows an eccentric path, slowing down as it moves away from the star and speeding up as it gets closer. So we can use this equation to calculate both the minimum and maximum orbital velocities of our planet by plugging in its apoapsis and periapsis values into the distance parameter, respectively. But before we get to that, we need to deal with the standard gravitational parameter, which is represented here with the Greek letter mu. This is just the gravitational mass of the system and is equal to the gravitational constant times the sum of the masses of our star and planet. And to make things a bit easier on us, we'll do this part of the equation first. So I'll go back to my calculator and start by entering the gravitational constant, in parentheses, 6.6743 times 10 to the power of negative 11. Then I'll multiply. Open 2 parentheses and enter the mass of the star. For me, that's 1.8023 times 10 to the 30 kilograms. Close parentheses, plus, open parentheses, and enter the mass of the planet. For For me, that's 6.6897 times 10 to the 24 kilograms. Close both parentheses and press equals. Since we're going to use this equation for 2 parameters, we will need this number again in a few minutes. If you're using the same calculator that I am, it has already been added to the history and can be recalled later. But if you're using a different calculator, you may need to employ its memory functions, or at least write this number down somewhere. With the standard gravitational parameter on screen, I'm going to multiply and open 2 parentheses. Then enter 2 divided by the planet's apoapsis distance. Mine is 131,333,633,660 meters. Close one parenthesis, subtract, and open another parenthesis. Then enter 1 divided by the planet's semi-major axis, or average distance. For me, that's 128,405,977,376 meters. Close both parentheses, and your equation should look something like this. Press equals, and then raise this number to the power of 1 over 2 to get the square root. Press equals again, and there's my planet's minimum orbital velocity. I'm going to add it to my SAP sheet as 29,917.20 meters per second. Now, to get my planet's maximum orbital velocity, I'm going to retrieve my standard gravitational parameter from the calculator's history and then multiply and open 2 parentheses. Then enter 2 divided by the planet's periapsis distance. Mine is 125,478,321,092 meters. Close one parenthesis, subtract, and open another parenthesis. Then enter 1 divided by the planet's semi-major axis and close both parentheses. Your equation should look something like this. Press equals, and then, as before, raise this number to the power of 1/2 to get the square root. Press equals again, and there's my planet's maximum orbital velocity. So I'm going to add that to my SAP sheet as 31,313.26 meters per second. If you made it through all that, congratulations! You now have a very detailed description of your planet's orbital characteristics.